Good afternoon, everyone, from your cousins across the sea. It's a beautiful day in Northern Virginia, and we're feeling the first rays of a warm spring sun beginning to coddle the earth. I understand it's not quite so pleasant in the United Kingdom, but hope you and yours are doing well, and that spring comes early and we all continue to emerge from what has been a very dark winter for pretty much everybody. But it's a dangerous world, and will continue to be a dangerous world as we emerge from the winter. There will continue to be a whole universe of problems for all of us to worry about. So how do we decide how to prioritize them, and which problem to address first, and how problems compare to each other? Well, you'll be glad to hear that there are methodical and logical ways to look at the challenges that we face every day in virtually every facet of life. That's certainly the case for looking at the challenges we have in PNT, GPS, and GNSS more generally. And for the engineers and technologists among you, you'll be glad to hear there is math involved. But before we get to the math, a bit of an English lesson first. Engineers, try to hang on in there for the next few slides. Words mean things and are important. And unless we get the words right, the math and the analysis will be for naught. So there are a lot of terms that are thrown around when we think about risk and dangers to ourselves. But the three most important words when discussing risk are you see here. When defining terms, it's often important to provide real-world examples, some context, and to help anchor ourselves in terms of definitions. So for the next few slides, we'll be thinking about these three words and this possibly exceptionally foolish person on the right here. I say possibly foolish because we really don't know what kind of risk they are taking. It's hard to tell how far off the ground they are and whether they're a teenager or a professional circus performer, and so on. But regardless, determining risk involves these same three things. They're the components of threat, vulnerability, and consequence. And I need to mention that this is a construct and a model that was developed by the folks I worked with in the United States Coast Guard and was then adopted by the U.S. Department of Homeland Security and is still in use right there now. So it's a good intellectual model, and I think it's a good analytical model as well. So again, in terms of definitions, threat. Any serious consideration of risk must be in response to the possibility of something bad happening or a threat. It's true that people do like to talk about the total risk to an enterprise, but analytically, the overall risk to something is just the aggregate of the risk from all possible threats. And we'll talk a little bit more about that later. But in our example here, there are a lot of risks to our tightrope walker. But to do an analysis, we really need to look at each threat vector and gauge how much of a risk it poses. One category of threats, as you can see on the right, might be wind gusts. And you can easily guess that there are different levels of risk for each wind speed. For our example, let's say, let's talk about a wind gust of 30 kilometers per hour. So now that we have sufficiently, we hope, identified the threat that we are concerned with, we also have to worry about vulnerability. How likely it is that the system under consideration is to be adversely impacted by a particular threat vector. So we should ask questions like, how good is our tightrope walker's balance? Do we have any data on how frequently he or she has fallen as a result of 30-kilometer wind gusts? And then the next one, the third piece in our risk equation, after threat and vulnerability, is consequence. So what are the bad outcomes that can result from this threat vector? These outcomes can be expressed qualitatively, in this example, by pain and suffering from broken bones, and quantitatively in terms of medical bills, lost income, and so on. And both of those approaches are good and useful depending upon their particular context and need. So risk is defined by these three terms. It's the probability of an adverse outcome, and it's defined by the product, and here's the math, ladies and gentlemen, or I should say maths, I suppose, for most of our viewers. It's the product of threat times vulnerability and consequence. So two probabilities plus the eventual bad thing that could possibly happen. So in our example, it's the probability of a 30-kilometer wind gust times the probability of a fall if there is a wind gust, and times the most likely damage that the person would incur. So let's presume that we've done all our research into all of the different factors, and we have some data that we can work with. We have found through our research, let's say, that there's a 20% chance of a 30-kilometer wind gust today. I understand in a lot of parts of the UK, there's about a 100% chance. But for right now, we'll say a 20% chance. We've also found, looking at the person's past performance, that in such conditions, they have a 10% chance of falling in these conditions, and that he or she has a 2% chance of broken bones. Therefore, this can be a useful computation, especially when comparing the risk from different threat vectors and across different activities. For example, before this presentation, I happened to have done a risk analysis for the same person driving on the M4 from London to Bristol. I found that that activity poses a 5% chance of broken bones from being in a motoring accident. So when comparing activities, if this person has a choice between walking a tightrope and driving the M4, they should always pick walking the tightrope. Now, it's also possible, as you may recall, and it's often useful to do this using a quantitative measure for consequence, usually in terms of cost. In this example, you see that the adverse outcome, in terms of broken bones, medical bills, and lost income, and so forth, is calculated at $15,000. So therefore, using the equation again and doing some relatively simple maths, we find that the risk of this particular activity for this particular person is $300. Well, how can we use that? Well, if this person was going to insure themselves against falling as a result of a 30-kilometer wind gust, $300 might be a fair premium to pay. Another way of looking at it would be that if the person was a paid performer, their fee should probably be something more than $300. So how can this be used in public policy decisions and larger issues like the ones that we're concerned about with PNT? You probably know that the city of Miami is always worried about hurricanes. So over the course of 5 years in this example, it's a virtual certainty that the city is going to be hit by at least one storm. So the probability is equal to 0. I'm sorry, the probability is equal to 1. So for those of you engineers who skipped the stats and probs course, you'll just have to take my word for it that 100% equals 1 in probability. So let's say that the Miami leaders have looked at the total vulnerabilities about the city and concluded that when a hurricane hits there, there's a 70% chance of damage totaling $5 trillion. So by doing our simple calculation again, we find that the risk is then $3.5 trillion. From a purely analytic point of view, it might make sense to spend up to that amount to reduce the city's vulnerability to hurricanes. Things like flood walls, hardened utilities, incentive for homeowners to install steel shutters, and so forth. Of course, hurricanes aren't the only threat vector to the city, so let's take another look at a Miami threat vector and what the consequent risk is. A lot of folks, especially in Texas now, are concerned about snowstorms and blizzards. Clearly, the risk is a lot lower and not a lot of investment is justified. So how can we calculate that? You can see that you can be calculated fairly easy right here, again, depending upon your assumptions. Of course, you always have to keep your risk analysis current. And with climate change and more volatile weather, well, you just never know. There may well be a significant risk of snow in Miami at some point. But that's the overall equation. Risk times threat times vulnerability equal times consequence. Risk equals threat times vulnerability times consequence. And this equation holds for pretty much any threat vector, be it from accident, natural phenomena, or intentional malicious acts. For malicious acts, though, while vulnerability and consequence are the same, We have to treat threat just a little bit differently. Since we are dealing with people, we must have an idea of how much they want to inflict harm, which we call intent, and how able they are to carry that intent through, which we call capability. So let's see how this would play out in a real life example. I know that all of you over there in the UK and around the world, along with me and many of my countrymen, are very concerned about the threat of Martian attack. And we really should be. I mean, Martians have laser weapons that can defeat any possible defense we could offer. So we are 100% vulnerable. And the consequences are dire. We will certainly all die in such an attack. And the Martians have the intent. They really, really do want to kill us. So we'll give them 100% on that score as well. Now, fortunately for all of us, they have not yet developed space travel. So their capability to carry out their intent is 0. And when we do the calculation, we find that in spite of all our vulnerabilities and horrible things that could happen and the Martians' desires, the risk for a Martian attack to us at the moment is 0. So let's hope that continues to be the case. Perhaps not the best example of a real-world attack, but you can imagine that there are defense and intelligence agencies that are doing these kinds of risk analysis all the time. There are bad guys that want to damage PNT, GPS, GNSS, and other critical infrastructure. A big part of the equation in all instances is how bad do they really want to do that. So to recap on our math equation, for natural events and accident, risk equals the threat times the vulnerability times the damage or consequence. And the malicious act, it's intent times capability times the vulnerability times consequence, also defined as damage here. So how do we do that when we think about PNT, or in this particular instance, GNSS? Well, in 2016, the R&T Foundation attempted to use this methodology and identified 22 different threat vectors for GNSS, as you can see right here. We then constructed the criteria for a qualitative analysis of the threats to each one posed by each one of those vectors. As you can see here, we did a numerical and color-coded structure and provided some qualitative definitions for each level of threat and consequence and vulnerability. And of course, we further defined it from malicious act down to intent and capability. A lot of this is based on things that have been expressed and can be detectable in the public, pretty much like an intelligence agency would do. But of course, we relied upon strictly open source media information to infer both intent and capability. Then, once we had the structure and the definitions all in place, we did calculations for each and every one of the different threat vectors. As you can see in this example, for moderate solar activity, we scored each one of the vectors in each one of the categories, did the multiplication, and came up with a risk score. And of course, the value of doing this is that you can compare the results to see how each of the different threat vectors stack up against each other. When you do a simple sorting, you can see how, as a result of the analysis that you did, each one of the threats compares. In this particular instance, as you can see at the top of the chart, we assessed that a year's total disruptions and economic damage as a result of criminal and privacy jamming equaled the overall risk from terrorist jamming and military style jamming. I'm not sure we would necessarily find that if we were to do this again, which reinforces the idea it's always important to keep examining your assumptions and reevaluating the data as it comes available. Another value of this, by the way, is that when you look at something like this, it gives you a good check on your gut. And if there is something that you intuitively see is wrong, you can go back and assess each one of the components of your analysis and say, where did I get it wrong? Or what could I change? What's a critical factor that would make this seem like an outcome that I would expect? Or conversely, you could look at that and say the results and say, oh yes, I see that now. I would not have guessed at that, but now that I see the rationale and the different components, it makes a lot more sense. As with a lot of analyses, this kind of thing is as important for the process that you go through as for the results sometimes. So, and speaking of, so we did this in 2016, and speaking of things that I think if we were to do this again, that we would do different, it would be to score major solar events a lot higher and a lot more significantly. And part of the reason for that is that there has been a lot more research into major solar activity in the last 5 years. We also need to keep in mind that these kinds of things and these kinds of numbers are very difficult to conceptualize and internalize in terms of the impact, to get a real personal sense of what they mean. So just departing a little bit from the analytical piece and moving on to the impact of the analysis, these numbers don't seem very significant right here for a major storm or even for a Carrington event. They seem like they're pretty low, and we might tend to say, well, not a big deal. Now, if we were to do the analysis and multiply everything out by all the incredible damage that would be done as a result of these, we might tell ourselves a different story. Another way of looking at it might be to think of this particular threat vector to GNSS and the possible horrible events, more like something like Russian roulette. So a major storm might be like having a revolver with 100 chambers in it, only 4 of which had bullets. So maybe we should imagine taking that revolver, spinning the chambers, and then pointing it at our knee. When the trigger is pulled, there's 4 chances out of 100 that we'll never walk again. And by the way, we don't have a choice about playing that game. The trigger is pulled for us every year on this for a major storm. So how do we feel about that? And is that enough of a risk? Is that enough of for us that we would actually go and take some steps to prevent the damage, to mitigate the risk by making ourselves more resilient to that solar storm? Same thing for a Carrington event, but of course this time there are 1,000 chambers in the revolver, and 7 of them are filled. But this time the gun's pointed at our head, and again we have no choice. The trigger's pulled for us every year. How do we feel about that? So those are the situations actually that are facing countries that have a severe over-reliance on GNSS for timing and location. And of course, that's only one threat vector. And the situation doesn't get any better. In fact, it gets a lot worse, of course, when you think of it over time. For a major storm, it's a 70% chance that we're not going to be able to walk again over the course of 30 years. And there's a 20% chance of early death. And let's not even look at the 100-year forecast. And we also have to keep in mind, as with any kind of statistical analysis and projection, that there are a lot of assumptions in terms of the data that we've been able to collect, that the events are random and independent, that past performance predicts future results, and any number of the things that could make the statistics faulty. Mark Twain used to like to say there's liars, damn liars, and statistics. And we have to really be careful that we don't let the numbers lie to us, or at least make us think things that we really shouldn't believe. We have to keep all of that in perspective. And as I mentioned before, human nature being what it is, we tend to think about only one threat vector at a time. These horrible numbers only apply to just one thing that could adversely impact or even terminate GNSS services. So the situation in terms of our needing to be much more resilient, reduce vulnerabilities, and so forth is a lot more dire even than the Russian roulette scenarios that we've talked about. So other threats, of course, are many and varied. Going to the completely opposite end of the spectrum is the threat of small jammers. And I say opposite end because instead of being very rare events, they're very common. They're daily events. And rather than devastating nations, the impact of these individual events are often impossible to measure because they're so small. Yet, as I mentioned before, if we could sum the negative impacts of all the millions of minor events, what might that total look like? Well, we can make a guess by doing some kind of risk analysis, and we can compare them and assess as to whether or not this is something we really need to protect ourselves against, or at least we can provide information to our assessment of whether or not we should take action to reduce our vulnerabilities. And of course, with this as well, we have to question what the assumptions, or at least understand what the assumptions we are making when we look at that data, how we interpret the sample size, and such as this is the information that's been collected by this Strike 3 project, and understand what's happening in a nation, or how we project and extend this sample size to the nation or the world as a whole. So there you are. There you have it in somewhat of a nutshell. This is a link to our 2016 paper. I recommend it to you in terms of a reference for process and a way to look at things more than for the actual results. And I hope it'll be useful to you. And I thank you for your time, and I look forward to questions and discussions afterward.